Have you ever just stared at the periodic table and felt like you were trying to read a different language? Just a big grid of letters and numbers? Well, forget all that painful memorization from science class. Today, we're going to treat this chart like what it really is, a secret code. A map. And on this map, an element's address doesn't just tell you where it tells you who it is and what it's about to do. And really, it all boils down to this one simple question. How is it possible that a single number, the atomic number, can act like a master key, unlocking an element's entire identity? We're talking its personality, its secrets, and how it interacts with literally everything around it. Well, let's find out. So here's our game plan. We'll start by looking at the code itself. Then, we'll learn how to place any element on the table and, just as important, how to figure out its identity just from its address. After that, we get to the really cool part, the secret behind chemical activity. We'll see it in action with some major element families and wrap it all up by understanding the incredible predictive power you get from this thing.
Okay, first things first. Before we can do anything else, we have to understand the basic logic of the table's layout. This is step one to cracking the code.
All right, let's get our hands dirty and actually crack this code. Our first mission is to learn how to put any element in its proper home on the table. And the key to all of this is its atomic number, the number of protons it has. We're going to use that one single number to find its exact address, its row, which we call a period, and its column, which we call a group. So how does this actually work? It's a really simple, logical four-step process. First, you figure out how an atom's electrons are arranged in their shells or energy levels. Once you have that, you just count how many shells are being used. That number? That's your period, your row number. Easy. Then, you just look at the very last outermost shell and count the electrons in it. That number is your group or your column number. Now, there is one little exception. If that outer shell is perfectly full, you're looking at a super stable noble gas, and it lives in group 0. And that's it. That is the core logic. Let's just lock in that first part of the address, the period number. A good way to think of it is like floors in a building. The more electron shells an atom has, the lower down it is on the table. So if you see an element in period 4, you know right away it's using 4 floors for all its electrons.
And now for the second part of the address, the group number. This one's even more straightforward. It is literally just the number of electrons hanging out in that final outermost shell. And you really want to pay attention to these electrons, because as you're about to see, they're the ones that run the entire show.
Okay, makes sense. We can get the address from the atomic number. But what if we flip that on its head? What if we only have the address, the period, and the group? Can we work backward to figure out what the element actually is? You bet we can. We just run the process in reverse. The period tells you how many shells you need to draw. The group tells you exactly how many electrons to put in the very last shell. Then you just fill up all the inner shells until they're full. Finally, you just add up every single one of those electrons, and that grand total? That's the element's unique atomic number. That's its identity. So we can pinpoint any element on the map. But so what? Why does any of this actually matter? Well, it matters because that location, that address, is so much more than just coordinates. It is a direct clue to an element's personality, how it behaves, who it gets along with, how it reacts. It is the secret to all of its chemical activity. The whole secret comes down to one concept: valence electrons. These are those electrons in the outermost energy level we keep talking about. You can think of them as the atom's ambassadors, or its frontline soldiers. They're the ones making connections, forming bonds, and driving every single chemical reaction in the universe. They control everything. So, here's the crucial point, the main idea. An element's chemical properties are almost entirely decided by how many valence electrons it has. And since the group number is the number of valence electrons, it means that every element in the same column has a similar chemical personality. They're family. Okay, now that we've got the theory down, let's see this code in action. We're going to take a look at a couple of these element families and watch how their shared address on the table creates these amazing, predictable patterns in how they behave.
We're going to compare two really famous families from opposite sides of the table. Over in group A1, you've got the alkali metals. These are super reactive metals. And way over in group A7, we have the halogens, a group of equally reactive but totally different non-metallic elements.
And this is where the patterns just jump right off the page. As we go down the column for both of these families, the atoms get bigger. That makes sense, right? We're adding more electron shells. But check out what happens to their chemical activity. For the alkali metals on the left, which are trying to give away one electron, their reactivity actually increases as you go down. Why? Because that outer electron is getting further and further from the nucleus, making it way easier to let go of. But for the halogens on the right, who desperately want to grab an electron, the exact opposite happens. Their reactivity decreases. As the atom gets bigger, its magnetic pull on a new electron gets weaker. This is the predictive power of the table, right here in action.
So let's bring this all home. What have we really learned? We've seen that an element's address on this table isn't just a random set of coordinates. It's a story. It's a story about its identity, its personality, and its destiny. And in the periodic table, everything is connected.
If there's one thing you take away today, it's this. The electron structure is the master key. It's what decides the element's place on the table, and that place, in turn, tells you almost everything about its properties and how it's going to behave. The periodic table isn't a list you have to memorize. It's a beautiful, logical system just waiting for you to understand it.
And I'll leave you with a final thought to chew on. Now that you understand the code, what could you predict about an element that humanity hasn't even discovered yet? I mean, if we found element 119 tomorrow, what family would it belong to? How reactive would it be? The amazing thing is you now have the tools to think like a chemist and make those predictions yourself. Thanks for joining me for this explainer.